Okay, thanks everyone, and thanks Mike. So we had a lot of discussion today during that workshop about understanding the solutions, and one of the aspects of the work we're pushing in our lab is making solutions more interpretable. So today I just want to chat briefly about a very recent approach we've developed to achieve just that. And I just want to acknowledge the main author here is Jonathan Ferrer-Mest. He's a postdoc with us and is the person currently diving next to the giant clam. And that's also work with Tom Dietrich and Olivier Buffet. Okay, so let's see if it works. Excellent. This paper was just presented yesterday at the ICAPS conference, so it's an AI conference. I'll give you the non-technical version as much as possible of that paper, and you can check the presentation there. So ICAPS is like one of the top AI conference, so one of the because we're trying to develop new algorithms to make applications of Markov decision processes or adaptive management more accessible, we do need to go through the phase where we have to publish in AI. And so these papers are quite dense, but it's a good sign that the science is strong. And once it's done, once we published in AI, we try our best to publish in ecology, but sometimes it's a little bit hard. Anyway, there's a paper for this work. There's a paper coming up that we're writing. Okay, so let me start with the beginning. To find the best strategy for a lot of sequential decision-making problem under uncertainty, we use Markov decision processes, and so adaptive management is also solved with the Markov decision processes. So that's all. You must be sick of its definitions, but it's important in that case of that. Our presentation, we have a set of states, set of actions, set of transition, and a reward function. And we would use that application for recovery of 200 species. It's the paper that Dave talked about at the beginning. We try to maximize the abundance of both species. And of course, it's a prey-predator relationship, and the states represents the abundance of CSIRO and the density of northern abalone adult population. And managers have to choose between 4 actions. They can introduce CSIROs into a system. They can implement some anti-poaching for the abalone. They can control CSIROs once they reach abalone. Once they reach their carrying capacity, or 80% of their carrying capacity, and they can do half of both things. So as a summary, if you had to understand what this presentation is about, if we solve that Markov decision process problem that we published in 2012, CSIROs and abalone problem, this is what our policy graph looks like. So so a policy, so the optimal strategy is a function S to A, okay. And then a policy graph, it's when in each state we apply, and in each state we apply the optimal action, right? So this is what it looks like. And because it's stochastic, it might look like that. So that's S1 and S2, okay. So it's convenient to understand what's happening here. And of course, we have a probability every time, let's say 0.5 here, of being successful, right? So it's basically a way of representing the P stars field in the result section of the MDP toolbox as a graph, or as a decision tree, if you want to call it that way. So what we propose, so when we show that to people, maybe don't know it. I don't know why, but so it's not very intuitively easy to understand. So what we're proposing is actually finding a way of representing simpler interpretable solution policy graph like this one. And the way we chose to do that, so there are potentially many ways of doing that, right? But the way we want to do that is by finding an equivalent MDP or close to equivalent with only K states. Here we go, that's our approach. And so the whole question is how to choose these K states so that the problem stays as similar as possible. So the motivation, can we increase models and solutions interpretability in human operating systems, right? So we want to generate a reduced state space MDP, so that's our KMDP, that minimizes the difference between the original optimal MDP value function. So that's a way of like, that's our performance here, or expected value, right? And the reduced optimal value function. So that's the new performance of a new KMDP. All right, so the things we need is an original MDP and the number of states the user would like to see at the end. So we're not trying to solve large MDP. It's not like approximate dynamic programming. This approach is suitable for actually small size MDP, I'd say, or relatively small size. What we are trying to find is the most compact Markov decision model and policy. So you can reflect on that. From my perspective, modeling is an art very often, and we do our best to get the information to model the problem in the best way possible. But what we're exploring here is like, is there an alternative way of solving exactly the same problem, but with less states? So here's what we're trying to, here's a summary of what we're trying to do is to decrease the number of states. So how does that work? Here we have number of states equals 4, and we asking our algorithm, I want only 2 states. And what it does is going to lump together. So we're going to have a new state SK1 and a new state SK2. And he will find out which states we should aggregate together. So it's in this part S1, S3, S2, S4. But he also needs to find out what are the new transition matrices and then finally solve a problem. Okay. So K MDPs, aggregate states without loss, that's our objective. There's a loss of optimality, but without too much loss of optimality. So if we look at the way we define KMDP, so we always kind of need some kind of formalisms, but it's pretty much the same thing as a normal MDP. The things that change is we have SK, so it's our reduced state space set, of size at most K. So at most K states, we can have less than K states at the end once we solve our algorithm. A doesn't change. TK is our new transition probability function, and we'll have to calculate that. And RK is also a new reward function. It's because our states space changes, we need to find a way to calculate these two information so that we actually solve the same problem. An important addition is that mapping function from S to SK. So this is like kind of a decision rule that will tell us how to aggregate or how to group these states. And of course, the optimal policy will be defined on, I think that's the next slide, but will be defined on SK instead of S. So we'll see that next slides. So because we're proposing a new a simplification, we go from an MDP to a KMDP. We need to find a way of evaluate what our solution, what our new solution would perform in comparison to, so that's our new solution would perform in comparison to the previous one. So this is what we're proposing. We're proposing to evaluate basically the performance of that new solution. So that's our optimal policy, given in the original MDP setup, right? So we apply or aggregated or simplified policy with the assumptions of the original MDP. So mathematically, if you're into optimization, or this is equivalent to minimizing a gap problem. We want to minimize the gap between the original performance or expected value MDP and our new, more compact solution. So we want to minimize the maximum gap in every state. So what we've done is design algorithms to do that. So what are the challenges? We need to know which state can be aggregated without loss of optimality, and we need to find a best mapping function. So that's like that mapping function phi, like the decision rules. When is it good to do that? From your perspective, the things you need to know is that's our algorithm here. As input, we need the original MDP. We need that decision rule of mapping function, and we need the user to tell us how many states we need. So that's our constraints here, the maximum number of states. And as an output, we propose, so it's the K MDP, so it's a new MDP only defined with K states, right? So tick. So I won't go too much into the details of what these algorithms are doing, but I think it's worth explaining a little bit how it works. So basically, our algorithms group states into bins, but we do that in a way that provides some performance guarantee. So if two states or more states are in the same bin, we say they can be aggregated. So our challenge is like how to define the size of a bin if we want K states. So it's not trivial because we want to have some performance guarantee about the way we do that. And we've divided several algorithms. Today I'm just going to focus on the one I think is most interesting and simplest for you to look at. It's what we call the phi A star algorithm. The important information here, these are like the decision rules. I'll explain that on the next slide. But the important information is that we have performance guarantee here. And so what it says is like the maximum gap is a function of the maximum reward in our system and our discount factor gamma there and a D here. So, and D is the size, D is this parameter here that will allow us to group the bin together. I'll explain that. So what our algorithm is trying to find is what is the best value of D that will guarantee the best performance overall. So let's just understand that simple. I think it's simple now that we found that we found these rules, but it wasn't simple to start with. So is our mapping function work? So we have a state I and state J. So these are states. And we put them in the same bin if they have the same optimal action to start with. We need to share the same optimal action. So that means I and J share the same optimal action. That's clear. And we also need that term here to be equal. So this is what's happened. So the V star of I is the original value of state I in the original MDP, right? So we need to add that value, and the V star of J is equivalently the optimal value for J if we in the original MDP problem. We divide that by D, so and we take the cell value. So as an example, if we have, so here we can look at we have 4 states. And we have 3 states that have the same action A2 and 1 state that is different. So we can, because our algorithm requires to have actions to be the same, we can only consider, so the first rule is like, we can potentially aggregate these 3 states together. Potentially we can go into the same state. Then we look at their value, at the value in each state. So we have 0.5, 0.4, and 0.36. We divide that by a factor D, and we get a number. I'm not sure what the value of D was there, but it's the size of a bin, basically. And we get these values. And then we take the cell value, so the the nearest upper integer. So we get that 4 and 3. Okay, so that means that we can group these two states S1 and S2, but we can't group this one. And even though for state S3 we have the same value, we can't group them together with S1 and S2 because it doesn't share the same optimal action. Okay, so this simple rule is the principle of give us a way of aggregating states together. And our algorithm is trying to find the best D for it, because the smaller the D and the better the performance, and the smallest the loss performance. And once we've grouped all the states together, we can, so that's what this algorithm is doing. Once we've grouped all the states together, what we do is we build our KMDP. So that's the thing we were trying to do, and then we can solve it. So I don't want to bother you. I think that's about all that is to say about the way these algorithms work. They have different rules. We tried many of them. It's more interesting to see the results from our perspective now. So that's the state space here. That's S in the original MDP problem. It's this two-state variable, so it's a two-dimensional problem. We have a density of northern abalone on the x-axis and the abundance of sea otter on the y-axis. And here we just represent the state space, right? The color corresponds to a different state, and we have 890 states. So I repeat, the color correspond to different states. They don't correspond to optimal action to perform. And so when we apply our algorithms, we end up with a solution that looks like that. This is our new state SK. And so we get good results, small loss of performance for 5 states. So if we apply our algorithm, we have good results for that. So let's, right now it looks like we're grouping the top there, the top space, this one state together, and then all of these there's something weird happening here. But if I was manager, I'd like to know why. But our algorithm doesn't allow us to do anything there. So there we go. So we looked at the state space. The next thing to do is looking at the policy graph, right? So this is a way of, it's a way of presenting the policy, including the dynamic, right? With the decision rule. Right? So this is what our original policy graph looked like. This is the original state space. With the number of states was 18 here, and now we have 5 state space. And this is what our new policy graph looks like for 5 state space. So to summarize, if you are in this area, you would introduce the other. If you have, and then you would do anti-poaching for quite some time. This is the different one. I'm saying for quite some time because it's like 0.8. You have a 0.8 chance of staying in the same state, so it's likely to happen for quite some time. And then you can go to different states. So SK5 and SK4 mostly. And so SK5 says continue anti-poaching, and SK4 says curl control sea otter. I don't know why it's harvesting here. It should be control sea otter. So that's wrong too. It's control sea otter. Anyway, we're not harvesting sea otter. Okay, so when we present that to our colleagues in applied ecology, they think it's promising. We've done some more experiments. So this is it's a one-dimensional problem. It's a control of a wolf population, and was published in the Maresco et al. Paper in 2013. We ran KMDPs with 3,000 states, and we were able to find a solution with 6 states. And for each of these states, this is what the optimal culling, I guess, or controlling or harvest is. controlling, I guess. So I think it's clear that way. If we look at what the optimal policy graphs look like, it's a nice, we can guess like a nice direction towards. So this is the states where the population crashes and we don't get out, and this is the population where this is the state where, or the direction towards where we have to start controlling the population every time in every state. We tried another fishery problem that is a bit more difficult to solve. And similarly, we were able to have some good reduction. So from 1,000 states to 13 states, we couldn't go further because the maximum number of states we can compress our MDP to has to be equal to the number of optimal actions. So in that solution, there was 13 different optimal actions. So that was it's one of the issues we have with our approach. So if you have 13 different optimal actions, this is the limit at which we can compress or aggregate our state space. And so because we have 13 states, the policy graph is a little bit simpler, but it's starting to be a little bit overwhelming from my perspective. Okay, so I just want to summarize. So the aim of that work is to propose to reduce the MDP states while minimizing the loss of optimality. So during this class, we saw that we could solve adaptive management problem using Markov decision processes. And then there's all this work that needs to be done about interpreting the results. I think this type of work could be really useful when it's time for you to actually communicate about the results of your study and for you to be convinced that this makes sense. So our aim here of all the research we've been doing has been to increase actually the uptake of these approaches, stochastic dynamic programming and Markov decision processes in human operated systems. And I think that's an area, especially if you work in conservation, where we're lagging, where we have a lot of, it's hard to use all these advanced tools because they're human operated systems. So you have to go through a stage where it's not a black box, it has to become a white box. We have to be able to interpret and explain the solution so that people are confident they understand why it makes sense. So as you've seen, it's from an AI perspective, it ticks all the boxes. From an applied perspective, there's way more to do. And so this is what we will be working on. So some of the things we want to focus is testing the interpretability of a proposed KMDP strategy. And for that, we actually need experts or people that understand MDPs to do a little bit survey with us. And I thought, oh, these participants at the workshop, they know so much about MDPs now. Maybe I can actually use their knowledge and actually get some of your time. If you're keen, send me an email and we'll add you to the study we are currently running. So that would be great. So the idea is to see whether or not you understand the strategy, if we are ticking the box and when we need to do more research. Of course, the challenge is when we have a high number of state variables. And so it's all about representation. And so I'd say these approaches work to a point. We need something more. Thank you, everyone.
So Iadine, you have one question in the Q&A. Do you want to look at it now or do you want to wait till the end?
Yeah, I can look at it. I don't know. Have it type. Sorry.
It's the second question.
Yeah, it's.
Have it.
Can you see it, or you want to read it?
Yes, are the types of adaptive management resource problems that lend themselves to reduced state solution methods? So that's a good question, and I would say in the adaptive management. So what adaptive management does is like we have an MDP that we augment with a belief state that is continuous. But what we know is that we can discretize the Markov decision process to solve it. And so with one of the approach that Paul that we've been working on is that discretization. So what I'm thinking here is that we can actually, in the same way, sorry. Can you see that? So in the same imagine that this is this Boom, boom, boom. Excellent. So yeah, in the same way that so what we do when, so if we just have an MDP, right, we just have a state space, right? And if we do the adaptive management, we augment the state space with our belief, right? So we're increasing the state variable, we have +1 there. So in resources, we just usually track the abundance of a population. So let's say that's your S here, and this could be your B, this could be your belief there, right? But we discretize. So my hope is that we can come up with something similar, right? You can like, so it's a coarse discretization, but it's very interesting to be able to have a policy graph, but we only need 5 states to represent exactly the same solution rather than something like that. Right? Because the size of a policy graph here is fixed. You will always have the number of nodes will always be 890. It's always going to be the number of states, right? So it's very hard to understand. And the number of arrows is the number of states you can reach based on that probability here. So if you can reach 2 states, then you have 2 arrows getting at. But if you can reach 10 states, that's 10 arrows going everywhere. So it becomes really hard to understand, right? So there we go. So I think it's promising. I hope I answered your question.
Karina has one more question in the chat.
Yes.
I
Can you
also
talk yeah. So Karina says, can you talk a little about the new transition priority matrices are calculated? Excellent question. That was the next level. Yes. So okay, so here we have to come up with a new probability transition functions and the new reward function. What we do is we just do right now it's an expected calculation. So we average all the transition priorities across all the states we group together. So if SK has 2 states, so we have S1 and S2, then we average the new probability of SK +1 to SK A with we do the average sum of the expectation of this thing, probability of the transition to S1, blah blah blah, and probability of transition to S2, blah blah blah. It's in our paper, it's available there, but it's just right now, so things to improve, right? We just these weights that we are using for each transition. Potentially there's a bit of work to do to find better weights. Right now they're uniformly distributed. We can do better work there, but it wasn't. It gave us good results like that, and that was simple.
I had a question I wanted to ask. This is a very interesting point, which I was thinking about. In general, when you're like collapsing a model, even if it's a matrix model, and you're collapsing some states, there's multiple ways to collapse the transition matrix. And so here, sometimes there's, depending on your goal, like you're looking for long-term dynamics stay the same or short-term dynamics to stay the same. So so here maybe it's long-term dynamics or
so here what we use what we call we use what we call a state abstraction function. Sounds good. Okay. So they call state abstraction function, and so they're ways of grouping state abstraction, the decision rule. And you are right. Because we have these results. These have been established. Some of them has been established in the literature for some time. We built on that to formally define our gap minimization problem here, right? So that we could could get a good performance guarantee.
Okay.
You are completely right. If you come up with, so what was interesting for us was some kind of performance guarantee around the value loss, and knowing that if, you know, this depends on that parameter D here, that R max. So there's also the gamma factor, exactly. So if we, if D is small, then that, if D is small, then this gap would be, the bound here would be smaller. Like we'll have a better, we minimize our gap, right? So that was interesting. And yeah, if you look at a different, if you have a different criteria than the one we're trying to minimize the gap, then you're likely to have come up with different value function. So what's interesting about this predicate 2 is that they are transitive, these ones and these ones. So they're transitive function. So this one isn't, and we have to solve, this one isn't transitive. I'm not going to bother you with it, but we have lots of fun developing some, because it's not transitive, it becomes a very interesting not cover click problem. And we've designed a really, really elegant algorithm that actually doesn't work. So we can just, so that was a lot of fun. We had lots of properties and stuff, but it can only solve very small problems. Well, these ones are definitely our best algorithm. That's what we're finding. So yeah. So I would say if you want to change the function, Suzanne, yeah, try to get transitivity as a property. That helps.
Okay, thank you. I think there's one more question just popped up in the Q&A. Can you see that, or you want me to read it? Okay. Can you see it? It's by Brian.
Paul asked about this, but in the CSIRO example, that checkboard pattern in the top left of the KMDP figure seems interesting and maybe spurious. Okay, yeah. So it's we have the same. Okay, so that's exactly the area. So I was alluding to that. So what happens with so it's you have to go back to the problem, the paper here. What happens as soon as we reach that carrying capacity? SK4, I think I can't remember. What are we doing? SK anti-poaching harvesting. SK4 we're harvesting, and SK4 and SK3 they have the same action. Yeah. So these two, we are removing CO2 from the. They reach a level where we remove CO2s from the population, and so if you go back to the paper, there's some oil spill occurrence that can crash the population of sea otters, and so that's a threat in British Columbia to sea otter population, right? So it kind of messes up the nice value, nice policy and nice value function. It's that you know, kind of shock event, like it's like, as Paul said, like it's a shock event. So there's no, my interpretation is like there's no clear rule in this area. In the paper, we talked about it as an alternative, as an option, like just to removing CO2 is very unlikely to happen in British Columbia because they're threatened. But we were trying to get both species at the same level of non-threatenedness, right? Getting them to recover at the same time. And so we didn't dig too much. We're just showing that it's not possible, basically. They need to change the way they're doing recovery for these two actions. Yeah, but it's because it's because of all the massive oil spill shocks that can happen at any time in the system. And so this is not a clear area. And it's the same thing with the optimal, with the original optimal strategy. I hope that answers that question.
Yeah.
Okay.
So yeah, these are very good suggestions. Sorry, these are very good suggestions in terms of interpretability. Right now we're just looking at numbers, and so we're just looking at like, do they share the same optimal actions, and do they have value functions that are quite similar? this is a first approach, and everything you're suggesting here, what about accounting for neighbors? All of these makes a lot of sense. And so, but it's finding a way of including that in our algorithms that is our next challenge. So there's lots of work around interpretability and explainability in AI. And so, yeah, that's, you're completely right. We need something else that helps us additional information, such as like, oh, they're close in numbers, to be included in that way of aggregating states. And that's our next challenge.